Dear students, today we will talk about 8086 instructions. So these instructions are basically used for programming 8086 microprocessor. An instruction is a binary pattern designed inside a microprocessor to perform a specific function. We have instruction to be defined in two different parts. The first part is opcode and the second part is operand. Opcode, it stands for operational code. It specifies the type of operation to be performed by CPU. Since CPU is able to operate or execute different types of instruction, so all these functions will fall or defined as instructions. It is the first field in the machine language instruction format. Example, we can define it like a MOV X and B, where X and B are either register or memory locations, whereas MOV is the instruction which is to be executed, the operation which has to be performed by the microprocessor. So all this MOV X, Y can be converted into 08 as an opcode. So this operational code will be understood as an instruction by microprocessor 8086. Operand, we can also say it as a data on which the operation should act. Operand is nothing but a data or an information on which the instruction has to be executed. The operands may be a register value or a memory location. The CPU executes the instruction using the information present in the field. It may be 8-bit data or 16-bit data sometimes. So the instruction set is a group of instructions which are basically used for performing operations by 8086. Mnemonics, there are a symbolic code for either instructions or commands to perform a particular function. These instructions are defined as a move, add, subtract, multiply, divide, and or etc. So all these are known as mnemonics. These mnemonics are used to define a complete instruction. There are different types of instructions available which is supported by microprocessor 8086. All these instructions are classified under these 8 different types of classes. So we have first as a data copy transfer instruction, second is arithmetic and logical instruction, third type set of instructions are known as branch instructions, then loop instructions. We also have machine control instruction, then a flag manipulation instruction, shift and rotate instruction. Then we have string instructions as well. The first set of instructions are known as data copy or transfer instructions. The example or the structure of this type of instruction is MOV Destination, source. This is the way we write an instruction. MOV is a instruction, the operation what a 8086 will perform. Destination and source are the two things on which the move instruction will be operated. There will be a transfer of data from source to destination. This is what the meaning of move source to destination. That will be written like move destination, source. Source can be a register, memory location, or intermediate data. Destination can be register or memory operand, a memory location to where the data has to be transferred. Both this is a condition that both source and destination cannot be a memory location or a segment registers at the same time. Segment registers, we know that CS, DS, ES and SS are the segment register. The MOV instruction can be defined with the following examples. MOV CS, 037AH, where 037A is a source and this source is in the form of data. This data has to be moved in the destination known as CX. So move instruction will copy or move the contents 037A to CX register. After executing this instruction, CX will hold 037A hexadecimal contents into this register. The same instruction move can also be used for 8-bit registers to transfer a 8-bit data. Here BL is a source, AL is a destination. This move instruction will move the contents of BL register into AL register. Then we have a third example as a move BX, in square bracket 0301H. So this square bracket represents the memory address. So whenever we have square bracket and the data in that is known as address, and the contents at this address will be moved to the register destination BX. So 0301 is considered as address and the contents of data at this particular address is copied into BX register, which will be done by the move instruction. Here we'll understand some of the examples. So move BX, AX. Here source and destination both are register. Source is AX, whereas BX is a destination. After executing this move AX, BX, AX, the contents of AX register, which are 2000, will be copied into register BX. So we also have another instruction known as move CL, M. M is a memory location. This M memory location will hold 40 as a data, 40 as a data. So this 40 as a data from memory has to be copied into CL register. CL is a 8-bit register. So after execution of these instructions, we have moved the contents of BX, AX into BX. Now AX holds 2000, so same contents will be copied from BX to AX to BX, so that BX will also hold the same contents as AX. So BX, after execution, the contents at BX is 2000H. Then for the second instruction, the contents of memory M 40 will be copied into register CL, that is CL after execution will hold 40 from memory location. Then stack pointer. Stack pointer, it is a 16-bit register. It contains the address of data from currently on top of the stack. Since stack is a data structure, stack will work as a first in, last out method. So whatever the contents pushed into the stack will always be pointed by stack pointer. Stack operations include pushing data on the stack and popping the data from the stack. So push and pop, these two operations will also be executed. So the data and transfer instructions has one of the instruction known as push source. So it only has one operand known as source. So source can be a register, segment register or memory. This instruction pushed the contents of specified source on the stack. In this stack pointer, it incremented by 2. The higher byte of data is pushed first, then the lower byte of data is pushed. Example can be defined as a push AX. So the contents of AX will be pushed into the stack. So stack pointer keep pointing to the data recently pushed into the stack. Second example is push DS. DS is a segment register known as data segment register. The contents at this data segment will be pushed into the stack. Push memory location 5000H. So the contents at this memory location 500H will be pushed into the stack. So this is an example which explains how does a stack operate. The stack pointer is currently pointing to this particular location. When we execute a push AX instruction, then the contents will be pushed into the stack where the stack pointer start pointing, it decrements, the stack pointer decrements and store the higher byte. The higher byte of AX will be pushed into the stack. Then it again decrements and store the lower byte into the stack. This is how the stack operates. This is a stack pointer, then the higher byte and the lower byte. This is an example of a push CX instruction. The SP stack pointer is currently pointing to 2002H location. So this is a memory known as stack data structure. So currently stack pointer is pointing to 2002H. So this is what the contents will be held by stack pointer 2002H. When we execute a push CX, CX is holding 10 in higher location, whereas CL in lower location of this register. So after execution of this push CX register, the contents of higher register CH will be copied into this stack data structure. Whereas now the stack pointer has been decremented. Again, the contents of lower register CL 50 will be copied into the data structure known as stack. Then the stack pointer is decremented and here the stack pointer is now pointing to 2000H. This is how stack and stack pointer instruction work. So this push instruction is already known. Now we'll move to the pop instruction. The pop operation is a second type of operation which is executed on a stack. Then pop destination is the structure of this pop instruction. Destination register can be a segment register or memory. So we will be copying the contents of stack segment into the destination. This instruction pops the contents of specified destination. In this stack pointer is incremented by 2. So whenever we move contents from stack to the destination, that time the stack pointer will be incremented. First, the lower data is popped first and then the higher data. This time the stack pointer is to be incremented. Example, pop AX, the contents of stack will be copied or moved to the register AX. The contents of stack will be moved to register DX. This is the operation move DX, sorry, pop DS. Again we have pop memory location 5000H is the memory location. The contents from stack will be transferred to this particular memory location. Now we will see how does it work. First of all, the stack pointer is pointing to this. So it will initial the position, read the lower byte first, then read the higher byte, and then the stack is incremented. So this is how we'll understand the operation or the example of pop BX register. The stack is holding the contents 30 and 50 at the location 2000H 2 and 2001H. Pop BX will copy the contents from stack to BH and BL, since BH and BL are empty and stack pointer is pointing to 2000H. After execution of this instruction, the contents of stack, that is 30 and 50, will be copied into the BH and BL register. First of all, now the stack was pointing to 2000th location. The contains 30 will be copied here into BL. Then stack pointer will increment. Then 50 will be copied into BH and stack pointer starts pointing to 2002H. This is how it works. This is a exchange XCHG destination and source instruction. So this instruction exchanges the contents of source with destination. So the contents from one register to another register or from memory location to register can be done. It cannot exchange. This is a limitation of a XCHG instruction. It cannot exchange two memory locations directly. The contents of AL are exchanged with BL. The contents of AH are exchanged with BH if we have the example as XCHG BX, AX. So AL to lower, higher to higher will be exchanged. We have another example as XCHG 5000 memory location to AX. The contents of this 16-bit will be exchanged with the AX. It means the contents of AX will be copied to this memory location and the contents at this memory location will be copied to AX register. The example is here. So XCHG AX and BX. So AH will hold at a higher 20 and lower 40, whereas BH will hold 70 and lower 80. So when we execute this instruction, the contents will be exchanged. So higher 70 to lower and then from lower to higher will be done. The next instruction is data transfer instruction with the port address. Port address is nothing but an address which is available to interact with the devices. It reads from a specific port address. So the port address is already defined. From this port address, the microprocessor will be getting a data in. So it copies the data to accumulator. Accumulator is AX from a port with 8-bit or 16-bit address. The port address can be 8-bit or 16-bit. So DX is the only register it allows to carry a port address. So many times the port address will be available in DX register. The examples are in AL, 80. 80 is a port address. The contents at this port address will be copied into AL. AL is a accumulator. In AX, DX. So DX will hold the 16-bit port address. the contents at this port address will be copied into AX register. This is an example of in AL80H instruction. AL is the port address is 80 and the content or data at this port address is 10. So this 10 will be copied from port address to AL register. So now this 10 is copied into AL. Another instruction is out 8-bit or 16-bit port address. So we have it writes to the specified port address. With the in instruction we get the data in, whereas with the out instruction we move the data or provide the data to a certain device through a port address. It copies the contents of accumulator to the port with 8-bit or 16-bit address. DX is the only register which allows to carry the port address. The examples are out 80 to AL. The contents from AL register, whatever is available, will be provided to the to the device which has a port address 80H. The contents at AX will be copied or provided to the port address DX with the example out DX, AX. With this example, we can understand the port address is 50 and the content at this port address has to be moved. So this port address, the contents at AL is 40. This 40 has to be moved to AL. We have another example as a XL80. So this XL80 instruction is a translate format from AL BX plus DS into AL, also known as translate instruction. It is used to find out codes in case of code conversion. It translates code of the key pressed to the corresponding 7-segment code. After execution, this instruction contents of AL register always gets replaced. So we have to move the already available contents from the AL register to somewhere else. So this XL80 instruction is the same. This is the only way the instruction will be executed. We also have some instruction known as LEA, LDS and load LES. So meaning are load effective address, load register and DS, load register and ES, where DS and ES are the segment register, data segment register and extra segment register. The format of this is LEA register, 16-bit register, whereas effective address. This effective address is nothing but the physical or the memory address which will be provided to the respective registers. So LDS are register, 16-bit register and memory address, whereas LES is the same way. We have memory address from where the register will be loaded. LEA 16-bit register source destination address. So we will understand how does the LEA work. Known as load effective address, LEA, it loads the effective address formed by the destination into the source address. So this address will be copied into BX or loaded into BX, whereas the address of BX will be copied into SI. LDS is known as load data segment register, whereas LES is a load extra segment register. These are nothing but the variants of LE, LDS instruction. So the examples of these are LDS BX, 5000, this is the address. So LES is a BX, 5000, this is again another address. So this is example of the. With this example, we can understand that the address provided 5000, the contains at this particular location will be copied into BX, whereas the next contains will be loaded into a DS or ES, whatever register we use in the instruction. LAHF. This instruction loads the AH register from the contents of lower byte of the flag register. The command is used to observe the status of conditional flags of flag register. So we can get the contents, or we can understand the status of the flag register with the help of this instruction. These instructions do not have any opcode. The EH register will be loaded with the flag information. The other way, we can also set the flags, conditional flags. Sometimes we need to control the flags. That in that way, first of all, we will load the AH register and then we will move this particular information with which the flag will be either set or reset using SAHF instruction. The push F instruction is used for the stack pointer. First of all, it will move all the flags to the memory location pointed by the stack. So sometimes we also want to store the contents of the flag register. So that time we will be using this push and pop instruction. If we want to copy the contents of flag register to the memory location, so push F can be used, whereas the instruction, if we want to copy the contents of memory location pointed by the stack to the flag register, that will be done by a pop F instruction. Thank you. This is how we understood first type of data move instructions. Thank you.